What you're looking at here is a 100 milliliter graduated cylinder that's filled with whole milk that I just purchased from the local dairy farmer. This is raw milk, which means it's not pasteurized. But even if it was pasteurized, you'd still see the formation of a cream line. Don't click away until you see the cream line. I promise something is happening in this time-lapse video. Let me tell you what's happening. Milk is an emulsion. Raw milk isn't a solution like sugar dissolved in water. This milk is an oil in water emulsion. Millions, actually billions of microscopic fat globules are suspended throughout the watery phase of the milk. Each fat globule has a milk fat globule membrane. Did you know that the fat had a membrane? Yes. That membrane is really unique, and it comes directly from the mammary gland cells, and it has phospholipids, sphingomyelin, cholesterol, membrane proteins, and glycoproteins. The membrane acts like a natural emulsifier, preventing the fat globules from immediately sticking together. And as a lagniappe, the cream is yellow because the milk contains natural occurring pigments, primarily beta-carotene, that gets concentrated in the fat. So that's when you'll see the yellow upper layer. But why do these rise anyway? The fat inside the globules has a lower density than the surrounding milk serum, which is mostly water. Because the fat globules are less dense, gravity creates an upward buoyant force. Why does it take so long? If you've ever looked through a microscope, an average fat globule is tiny, like 2 to 5 micrometers. It's like a tiny balloon trying to float through a really dense liquid. And that's why the cream separation takes hours instead of seconds. What happens as they rise? This is really the cool part. So initially, every fat globule is moving independently. Remember that cool membrane? As more and more globules reach the top, they become crowded. The cream layer becomes increasingly concentrated. Some globules start to gently bump into each other. Because each still has its membrane, they don't immediately fuse into one giant droplet like you might expect. Instead, they form a densely packed layer having the fat globules, water, casein, micelles, whey, lactose, and minerals. So the cream layer is not purely fat. It's simply the region where the fat globules have become highly concentrated. Now, why doesn't homogenized milk do this? Homogenization forces the milk through teeny tiny openings at a very high pressure. That shatters the large fat globules into many tiny ones. It reduces its size a great deal. So let's say by a fifth, and that would make it rise at 1/25th as fast. The fat's still there, but now the globules are so small that they remain suspended for weeks or months. So you never see a cream line. Here, you can see the cream line forming at the 80 mil mark. If you do the math on this, this means that this particular milk is about 5% fat. Wait, it's at 80 mils. Why wouldn't it be 20%? Well, that's because the cream is not all fat. It's only a percentage fat. And back of the envelope calculations tells you it's about 5%. Now, one final interesting thing. We started at 100 milliliters, and you saw that over time. But look where the milk is now, right? It's over 100 mil. And that's because the fat and particles trapped inside it are more buoyant. So it now looks like we have more than 100 mils of fat. Find the creamline calculator on the Joy of Cheese website tools site. There's a lot of cool Joy of Cheese tools at the Joy of Cheese website. Bye.